In the previous videos, we have seen some of the constructs used for flow control. For example, branching structures, for loops. They are kind of flow control constructs. Now let's look at how we can actually sort of manipulate some of the basic data structures provided by Matlab. We started to work on the matrices in the previous video, right? And we looked at some of the basic ways for creating matrices in Matlab and how do we actually do matrix multiplication by using nested loops, and also how to do matrix multiplications by using Matlab's built-in multiplication operator. But now let's talk a little bit more about those data structures, about those containers, right? And then the most fundamental container or most fundamental data structure provided by Matlab is actually the matrix. And Matlab was originally called the Matrix Laboratory. It started as a software for manipulating matrices, basically, right? It was a linear algebra. It was a linear algebra software. It was built as a tool for doing linear algebra calculations. And because linear algebra is used very widely, both in academia and in industry and in many kinds of applications, so that's one of the reasons why Matlab actually eventually become so universal and so widely used, right? So in this video, let's start to understand this very fundamental data structure, right? A very fundamental data structure, and we will start by looking at vectors. In fact, a vector is a kind of a matrix, right? It's just a matrix with just one row or one column, right? So how do we actually create and manipulate vectors, right? So we're going to work towards the solution of this particular problem: analysis of the elements of a vector, right? And again, this is an example taken from our textbook, right? It's example 2.1. Given the following function, which is ft equals to sine of t, and t goes from 0 to 2 pi inclusive, right? From 0 to 2 pi. And then for 50 equally spaced values of this function in this region, which means that we need to actually sample this particular function in this interval using 50 points, 50 evenly spaced or equally spaced points, basically. We shall a determine the time, so t is treated as a time here, determine the time at which the minimum positive value of ft occurs, which we will need to find the time at which the minimum positive value, so ft must be positive, and then we need to find the minimum value of that all the positive values, the minimum among all the positive values of ft, and then find its time location, right? And then b, the average value of its negative values. So we need to identify all the negative values of ft, and then get the average of those negative numbers. So that's sort of the question. That's sort of the problem that we will try to solve, right? And so if you have no idea about what how to actually create and manipulate the vectors, solving this problem using Matlab seems to be quite difficult, right? So let's work towards that one step at a time. We're gonna start with simple operations for creating vectors inside Matlab, and then we will look at how we can actually retrieve values from vectors and how we can actually compute those kind of statistics on those vector values, right? So let's create a new script first. Let's create a new script first, and then write a command. Basic vector creation and manipulation. Right. This is a script that we're we're going to use to demonstrate how to use vectors, right? So the first thing we're going to talk about is vector creation. How to create vectors, right? How to actually creation of vectors. Creation of vectors. Probably the most fundamental way for creating vectors is just by typing the numbers into a pair of square brackets. So v1, let's call it vector 1 equals to 0, 1, 2, 3, 4. Right. So this is basically creating a vector with just 5 different values that goes from 0 to 4. Right. And then we're assigning it to the variable name v1. So v1 is going to be a vector with 5 columns and 1 row. Right? And all the values goes from 0 to 4. And if we run this code, let's give it a name, vector operations. And then after we have finished running this code, if we in the command window, if we type v1, you're going to be able to see its content, right? And it's actually displayed as a row vector. Right? And the reason that it's a row vector is because we're separating all the elements with a comma. Right? If you would prefer to use just a space without typing comma, this extra character, you can just separate all the different elements by space. But the result will be identical. There's no difference actually. If you run it again, and then look at v1, it's still a row vector, right? It doesn't actually change anything. So you can use either comma or space to separate the different columns inside of this vector, right? But suppose we do v2, it's gonna equal to 0 semicolon 1, 2, 3, 4. Right? Suppose we do this thing. So every element inside of this vector is separated by just using a semicolon. It's not a comma, it's not a space, but it's a semicolon, right? This space is actually optional. You can use a space or not. It doesn't really matter too much, right? But if people prefer to put a space here just for kind of a readability of the code, but the space is actually optional if you are using a semicolon. And then let's run it again, and then we have both v1 and v2 now, and you can sort of see v1 and v2 are displayed differently inside the command window. So v1 is displayed as a row vector, but v2 is actually displayed as a column vector, right? So semicolon is used to separate the different rows, of the same column, right? We looked at this kind of distinction when we try to create a matrix or type up a matrix in our previous video, right? So there's this kind of distinction between using a comma and a semicolon, comma or space and a semicolon, right? So if the vector that you are trying to create has some kind of pattern, for example, for v1 or v2, the number keeps increasing, right? Goes from 0 to 4, and every time it actually is the element value actually increases by just 1. Right? If the vector has some kind of pattern, you may have you can construct the vector using the so-called colon operator, the range operator, colon operator, colon notation. Right? So let's do v3. v3 is going to equal to 0 colon 4, right? So in the previous videos we were saying that this is sort of some kind of range operator, right? So this the number in front of the colon is the starting value, and the number after the colon is the ending value. So v3 basically has a so if we run this code and then type of v3 basically goes from 0 to 4, right? 0 is the starting value, and then 4 is sort of the ending value, right? And by default, this kind of vector that's created is automatically a row vector. If you are using this colon notation to create a vector, the the vector is by default a row vector, right? But if you would like to actually have a column vector instead of a row vector, what you can do is to and then wrap the whole thing inside of a pair of parentheses, right? And then just put this single quote after this parenthesis, and then you'll be able to actually create a column vector, right? And this single quote actually means transpose. So if you haven't actually used the transpose before, you can type help transpose. It's also a Matlab intrinsic function, right? Transpose is a non-conjugated transpose, so it's a dot one single quote, right? Dot single quote. But here we are not really doing a dot because it's not really necessary, right? So if we run this code, and then look at v3, that's a row vector, right? But if we look at v4, that's a column vector, right? So every time if you try to actually use the colon notation to create a vector, the default output is going to be a row vector. If you want to obtain a column vector, all you have to do is to actually transpose the vector that's created by using this colon notation. So by default, if you are just using a single colon or a single range operator, by default, the kind of step, the so-called stride, right? So, but in principle, it's in mathematics, it's just an increment, right? The increment from the starting value to the ending value, the increment for every element between the starting value and the ending value is by default 1, right? So from 0 to 1, the increment is 1. From 1 to 2, the increment is again 1. From 2 to 3, the increment is still 1, right? And then from 3 to 4, the increment is still 1. So by default, the colon notation is going to give you a sequence, a vector with its element incremented by just 1, right? The increment by default is 1. But suppose you want to use a different kind of a value for the increment. How can you actually do that, right? How can you actually specify a increment value that's not unity, right? Suppose we would like to actually create a horizontal axis. X goes from like from point 2 to 1, right? But we want the increment to be 0.1. So that's what we can do, right? So again, starting value, ending value, and then the number sort of in between the two neighboring colons is actually the stride. You can specify a stride that's not unity, right? So now if we run this code, then it goes from 0.2 to 1 with a stride or with an increment of 0.1. So 0.2 plus 0.1, that's 0.3. 0.3 plus 0.1, that's 0.4. 0.4 plus 0.1, that's 0.5. Right? And this is also a very convenient way for just creating a sequence of numbers with a fixed increment, right? And this increment value doesn't have to be a positive number. It can be a negative number. If it's a negative number, then it's not increment, it's decrement, right? It's decrement. Decrement. Say suppose t equals to point. I'm going to write something that's incorrect. Right. So the starting value is 0.2. The ending value, which is bigger than the starting value, right? So it's 0.2 here, but ending value is 1. And then if we specify a negative increment, then what's going to happen, right? Let's give it a try and see what's going to happen, right? So x is still correct, right? But what about t? Matlab tells us that the t that's created by using this colon operation is an empty row vector, right? Why it's an empty row vector, right? So if you start from 0.2 and then with a negative stride of minus 0.1, you will never be able to actually reach the value of 1. It's impossible, right? If the starting value is 0.2, then and the stride is minus 0.1, then the next number in the sequence is supposed to be 0.2 subtract 0.1. That's supposed to be 0.1, right? It's smaller than 0.2, right? So there's no possibility of reaching 1, right? So that's why Matlab is telling you that this t vector is going to be empty, because this is an impossible sequence, right? So how do we actually make it work, right? How do we actually make it work? What needs to be changed, right? All we need to do is to actually switch the starting value and the ending value, right? So now we start from 1, and then with a stride of minus 0.1, and then we end with the value of 0.2, right? So 1 subtract 0.1, that's 0.9, and then subtract 0.1 again, that's 0.8, right? Until we reach 0.2, right? So let's run this one again, and then let's look at t again. So 1, 0.9, 0.8, 0.7, and then down to like 0.2, right? So you can have a negative stride or negative increment, right? And there's a quite useful function that allows you to actually sort of examine the length of a particular vector, and the name of the function is just called length, right? It's just called length. So suppose you would like to know what's actually the length of t, for example, right? What you can do is to call the length function. And then let's call it n. The returned value is n. Let's run it, right? And then n is gonna have a value of 9, which is exactly the number of elements inside of the t vector, right? And this length function applies not just to row vectors, it also applies to column vectors. So if you transpose t by doing this single quote thing, and then the result is still going to be 9, right? And it still has a value of 9. So it's applicable not just to row vectors, but also to column vectors, because t prime is exactly a column vector, right? It's a column vector. Sometimes we would like to create a vector that's so now let's look at some limitations of the column notation. Suppose we would like to create a vector that's let's say the y equals to 0.22, and then m equals to the length of y, right? And let's try to understand what this piece of code is going to do, right? Again, we want the y to be a vector that goes from 0.2 to 1. But now the stride 0.12, the increment, is not sort of a number that can actually allows you to go from 0.2 to 1 in a finite number, or in an integer number of steps, right? So what's gonna be the value of y, right? What's gonna be the values inside of y? If we look at the y, so y started with 0.2, right? And then because the stride is 0.12, so the increment is 0.12, so the next number should be 0.2 plus 0.12, that's 0.32, right? And then the next number is 0.32 plus 0.12, that's 0.44, right? That's exactly true. But as you increase gradually, eventually it's gonna reach 0.92, right? Then what's gonna be the next number, right? What's gonna be the next number? 0.92 plus 0.12 is what? That's 1.04, right? So 0.92 plus 0.12. That's 1.04, right? And 1.04 is larger than 1, right? and then you specified using this range operator, using the colon notation, you specified the end value to be 1, right? So when MATLAB actually sees that 1.04 is larger than 1, it's gonna stop generating generating more numbers. So it's gonna stop at 0.92, right? It won't actually reach 1, right? The ending value is not gonna be 1, right? The ending value is gonna be at a value that's smaller than 1, right? But if you actually try to add the increment to this number, it's going to immediately exceed the ending value, right? So that's sort of the behavior of MATLAB's colon notation, right? But sometimes what we would like to do is to actually have a fixed starting value and then a fixed ending value. We would like to stop the sequence at that particular ending value. Right? What we do not care about is actually the stride, it's actually the increment. We don't really care about how large the increment actually is, but we do want our sequence to have a fixed starting and an ending value, right? And if that's the case, if that's what we want to do, there's a different way for creating the sequence, for creating the vector, right? Generation of equally spaced values, and the function that we're going to look at is called linkspace. It's called linkspace. So suppose let's call it x1 equals to linkspace 0.2 1, and then suppose we want like a so what's actually the length of y? What's actually the value of m7? So suppose we wanted 7 values, right? And again, linkspace is actually a Matlab intrinsic function, and this linkspace takes 3 inputs as 3 arguments as inputs. The starting value 0.2, right? And then the ending value. Right? But the third input is not the stride. The third input is the total number of points you want for this generated vector. So now if we run it, and let's take a look at the values inside of x1. Right? And x1, let's compare it with y. Right? Both of the sequences have exactly 7 numbers in it, right? And then both sequences actually starts with the same starting value, 0.2, right? But for y, but for this vector y, the stride is specified by the user, right? So we're specifying this fixed stride. So y will not be able to actually reach 1 as its ending value because the stride is kind of fixed, right? But in linkspace, when you actually use linkspace, the last input is actually the total number of points you want, right? So Matlab is going to automatically compute the appropriate stride, right, based upon the number of points you want, and also the starting and the ending value, right? So the stride is not specified by the user to a fixed value. It's going to be automatically computed by Matlab. And then what's going to be the formula for computing that stride, right? So if you want like 7 points, if you want exactly 7 points, then the number of intervals between the neighboring points is 6. It's 7 subtract 1. It's 6 points. So what Matlab is going to do is that it's going to take the ending value and then subtract the starting value. That's 0.8, right? So 1 subtract 0.2, that's 0.8. And then it's going to divide 0.8 by 6, which is basically the number of points you want, subtract 1. Right? So it's 0.8. Let's in the command window, let's define a new variable that's called s equals to 1 subtract 0.2. Right? That's the ending value, subtract the starting value, and then divide 7 subtract 1. Right, that's 0.1333, right? With lots of 3s behind it. So suppose suppose let's copy this piece of code into our script and then generate another sequence, right? And then generate x2. X2 is gonna start from point 2, and then with this s as its stride, and then end with 1, right? And then we can compare x2 with y, right? Oh, we can compare x2 with x1, I mean, right? Let's run it again. So x1 was created by using linkspace, right? So it goes from point 2 to 7, point 2 to 1 with exactly 7 points. And then x2 is created by using this colon operation, colon notation, right? And then this stride is computed by ourselves using this particular formula. And you can sort of see both of them are actually identical. So x1 actually equals to x2, right? And what linkspace actually does is just like that, right? So internally, linkspace basically just computes the stride based upon the number of points you want and the starting and ending value that you want, right? It computes the stride and then just create the vector by using this kind of colon notation, right? But it's actually doing that in a more efficient way. It's good. But in principle, it's kind of in theory, it's pretty much the same, right? So linkspace allows you to specify the starting and ending value and then the total number of points you want, right? It's so if you would prefer to use this kind of colon notation, you can just do this calculation by hand, right, manually, and then you can use the colon notation, and then you specify the stride to the appropriate value, right? But linkspace just provides a wrapper around these 2 lines of code, basically. And again, if you want to sort of specify, let's create a linkspace. So suppose the starting value is like 8, and then the ending value is 2.5, and then let's create like 10 points, right? Then it's gonna have a decrement. It's gonna automatically compute the decrement, right? The stride is, in this case, the stride is gonna be a negative number, right? And linkspace doesn't really require you to compute the stride or input the stride. It's gonna automatically compute the negative stride for you. Sometimes we would like to actually create equal space on a logarithmic scale, right? In some applications, we would like to actually create a sequence of even spacing on a logarithmic scale, right? So if that's what we want, Matlab actually has another function called a log space. It's called log space. And then let's give it a try. So let's start from 0, 2 with 5 points, right? Let's see what log space is gonna create. Right, x4. So the first element in x4 is gonna be 1. Why it's 1, right? The first input to the log space is gonna be treated as a starting value of the power to 10. Right, so it's 10 to the 0th power, right? And then that's exactly 1. And then the second input is going to be treated as the ending power of 10. That's exactly 100. So this x4 is going to have a value that goes from 1 to 100, right? And then we want like 5 different points. So 1, 2, 3, 4, 5. 5 different points. And all this kind of spacing is kind of a sort of evenly distributed in a logarithmic space. So what exactly is so suppose 1, 2, 3, 4, 5. What's actually so if we do a linkspace 0 to 2, 0 to 2 at 5 points, then it's going to be 0.51, 1.52, right? So So how it's gonna work out? So it's 10 to the 0.5 power. That's 3.1623, right? Is that the second element? 3.1623, right? That's exactly the second element. And then that's 10 to the first power. That's 10, right? And then 10 to the 1.5 power. Then 31.6228, right? 31.6228, and then 100, right? So basically it's a link space between 0 and 2 with 5 points, and then you apply the resulting sequence as the power of 10. This way you get the evenly distributed spacing in the logarithmic space, right? And that's link space and log space, right? Link space and log space, very useful functions for us to create vectors based upon different kinds of specifications. So those are some of the capabilities for creating vectors, and later on, once we start to create matrices, we're going to be able to see that there are more functions allows you to create vectors and matrices. Vectors are just a special kind of matrices, right? Later on, we're going to talk about how to create matrices using some of the built-in intrinsic functions, right? But now let's look at how we can actually access the elements of those vectors, right? So a vector is basically just a container with lots of smaller containers inside of it, right? And all those smaller containers are just arranged in this particular sequence, right? And then if you want to sort of access not the vector itself, but individual smaller containers inside of this vector, right? You have to sort of use the index. So here in the command window, we are basically just accessing in all our commands that we have typed so far. We're basically just accessing. If we want to look at the vector itself, then we just type the name of the vector, and then Matlab is going to display the content of the entire vector. It's not the one element of it. It displays the vector in its entirety, right? So that's the vector. A vector is sort of different from the elements inside of that vector, right? So if we would like to actually retrieve a specific element inside of a vector, we have to use a index convention. We have to use the index convention, right? So accessing elements of vectors, right? So if Matlab has a convention that every index must start the smallest index that you can access is 1, right? So you cannot have negative index or 0 index. This is different from C or Java, right? C or Java, right? In C or Java, you can have 0 index, but you cannot have negative index. But in Fortran, if you have used Fortran before, those later versions of Fortran actually allows you to have negative and also 0 indexes, right? But in Matlab, you cannot do that, right? The index is always a natural number. It has to start from 1. So suppose you would like to actually display the first element of x4, or then what you have to do is let's just do a disp, right? X4. Then what's gonna be the index for retrieving the first element of x4, right? That's 1. Right? So x4 with the parenthesis 1. That's gonna allow us to actually retrieve the first element of x4. Right? If we run it, the first element of x4 is 1. Right? That's 10 to the 0th power. So how do we actually retrieve the last element of a particular vector, right? Suppose we don't really know what's actually the length of the vector, right? What's going to be a convenient way for us to actually retrieve the last element of a vector? Suppose x4. So Matlab provides a keyword called end, and this end is a kind of a shorthand notation for you to actually index or to retrieve the last element inside of a vector. So if we run it, you're going to get 100. Right? 100 is 10 to the second power, right? That's 100. And this n is actually equivalent to accessing. Suppose you know the length of x4, right? Suppose you know even if you don't know the length of x4, you can use the function length that we have seen before, right? The length, if you use x4 as input to the length function, and then this length function is going to return the total length of x4, right? Which is supposed to be 5, right? So length x4 is going to be 5. So basically you are actually accessing x4, the fifth element of x4, right? So it's still going to work. That's 100, right? So n is just the equivalent to calling the length of x4, right? And which is equivalent to the last element of that particular vector. And then when you actually try to, we looked at how to use the colon notation to actually create vectors, right? When we try to index into a vector, we can also use the colon vector. We can also use the colon notation, right? Suppose we would like to actually retrieve the second to the fourth element of x4. What we can do is to 2 colon 4, right? So if you do this, then it's gonna retrieve the second element, the third element, and then also the fourth element. And the output, the result of this particular call, this particular the highlighted portion, is another vector basically. So in principle, you could actually assign x5 to, right, and then this x5, right, and the result is exactly the same, right? And again, because you can use colon notation, right, so it allows you to actually specify a stride, right? Suppose the stride is not 1, it's not 1, we want the stride to be 2, for example, right? So how do we actually do that? Suppose we want from the first element to 2 to end, right? We want all the odd numbers, all the odd indexes, odd containers, all the odd indexes, right? And then this x6. Then it's gonna retrieve the first element, the third element, and then the fifth element, right? If you look at x4, the first element, the third element, and then the fifth element, right? So it starts from the first element, end with the last element, and then with a stride of 2, right? So it's the first element and then the third element, first element, third element, and then 3 plus 2, that's 5, so the fifth element, right? So you can actually index into a vector by using the colon notation also, right? And then we looked at the first element, right, the last element, right? If you want to access, for example, the second element, then it's just x4 2. If you want to access the third element, then it's just x4 3. And all those indexes must be wrapped around inside of parentheses in order to actually access that particular element, right? And MATLAB also provides some functions, for example, for you to actually sort vectors, for you to actually specify, for you to actually select elements based upon certain kind of a conditionals, right? Certain kind of a conditional tests, for example, right? So if you would like to actually, let's create a random vector, for example. Let's create a random vector. No, it's not a good idea. It's called vector operators, right? So let's say v2. We have used yeah, we used the v2. Let's use v5. v5 equals to rand. Rand is again MATLAB intrinsic function, right? And if you would like to try help rand, you will be able to actually see what this rand function can actually create, right? So So if you call rand with just a one input, then it's going to return a n by n matrix, right, containing all the pseudo numbers. Right? But if you would like to actually create a vector, right, then you have to specify two numbers wrapped inside of a square bracket. So let's do that. Let's create a random number with one row, 5 columns. And then v6 is going to equal to sort v5, right? So v6 is going to be a sorted version of v5. So v5, that's a sequence of random numbers, right? And then v6 is going to be this random number sorted in the increasing order, right? And then this sort function also has a manual page if you would like to actually investigate how to use this particular sort function, right? You can apply the sort function not just to a vector but also to a column, to a matrix, right? And then you can sort of specify the dimension on which you want to sort. And then you can also specify a direction. So if you want a ascending sort or descend sort, right? Suppose by default it's ascend, right? That's the default sorting. But if you would like to actually sort all the numbers in a reversed order, let's just copy that descend. Let's just so say v7 equals to sort v5 and then descend. Hope I spelled this thing correctly. No, I spelled it wrong. D-S-C-E and D, not T. E and D, descend. That's right. Then v5 is still this kind of a random number sequence. v6 is going to be sort of sorted in the ascending order, and then v7 is going to be sorted in the descending order. Right. And that's how you can actually sort it, right? And in addition to that, MATLAB also provides a very special kind of function that's called find, right? Find is a function that allows you to actually select elements based upon certain condition. So suppose I generate an index vector called idx using the find function. I would like to find v5 that's with all the numbers that's larger than or equal to 0.5, suppose, right? So again, let's run it. So v5 is the 5 random numbers, right? 0.14, 0.42, this kind of thing, right? But we have like this number, and this number, 3 numbers that are larger than or equal to 0.5, right? Let's see what's actually inside of IDX. IDX is actually the index of those elements with a value larger than or equal to 0.5, right? That's 3, 4, 5. So 1, 2, 3, 4, 5, right? So suppose we do v8 equals to v7 IDX. Then what's going to be inside of v8, right? v8 are going to just contain the 3 elements that's larger than. Oh, I see. Because the random number is not kind of it's generated random. Every time I run this script, it's going to regenerate all the random numbers. So v5 this time is going to have like a the first element, the third element, and then right. So v8 is going to be what? v7 is already, it's not, so I wrote the code wrong. It's v5 IDX, right? Sorry. So v5, that's and then v8, right? So the numbers that's smaller than 0.5, the numbers that are smaller than 0.5 has been filtered out, right? And all the numbers that goes into v8 are those ones with with a value that's larger than 0.5. And sometimes we can just sort of combine these 2 lines of code into just one line, right? So here we're explicitly creating this particular index, and then use this index to index into v5, right? But in principle, we don't really have to explicitly create this index. So what we can do is to just cut and paste. Let's cut this line of code, and then just paste it inside of the parentheses. And then if we run the same, run this code again, that's v5, right? And then v8 is gonna be, okay, so most of the values are actually smaller than 5, smaller than 0.5, so it's just gonna retain one of those elements, right? Because the rest of the elements are all smaller than 5, right? So you don't really have to explicitly create a index, right, by using the find function. But if you actually look at the kind of for now, this there's a small kind of orange wiggle line underneath the keyword the function name find, right? Which means that Matlab is actually trying to tell us something about this particular line of code. So if we move our cursor to that, it's going to give us some hint about what exactly can be done. So if v5 is an indexed variable, performance can be improved using logical indexing instead of find. Right. So it means what? It means that essentially you can remove this find call. You can just get rid of it, and then also the parentheses that's associated with this particular function call. Right. You can just use this kind of a conditional. This kind of conditional test, which is going to return either true or false, right? As the index that goes into this parenthesis for selecting v5, right? And if you run it again, so v5 and then v8, right? It's still giving you exactly the same effect. All the values that's larger than or equal to 0.5 are being selected. And internally, this line of code is just equivalent to using the find function, right? But you don't really have to use the find function to implicitly or explicitly generate the index. It's the index is kind of used implicitly here, right? And then this comparison operator larger than or equal to is applied on what? It's applied on the vector, right? It's not applied on individual elements. It's applied on the vector and this particular scalar, right? So what this operator is going to do is that it's going to compare every element inside of this vector with this scalar number, and if the condition is true, if the comparison actually returns true, then that particular element inside of v5 is going to be selected, right? And if the comparison actually returns false, then that element is going to be rejected. So this conditional, you can think of this particular conditional as some kind of creating some kind of a mask array, and this mask array has exactly the same length as v5, and depending upon the values inside of v5, this mask array is going to have true or false as its values, right? And if the value is true, if the value inside of the mask array is true, then this vector, which happens to be v5 again, the corresponding element in this vector is going to be selected and then goes into v8. Right? And if it's false, then the corresponding element inside of this particular v5 vector is going to be rejected and will not go into the v8 vector. And then Matlab also provides a few more functions that allows you to find the minimum and the maximum value inside of the vector. And the name is actually quite easy to understand. It's just called max or min, right? Again, let's so let's call it vmax. It's going to equal to max v5, right? So max is again Matlab intrinsic function. If you give it a vector, and then the max function is going to return the maximum value inside of that particular vector, right? And then you also have a min function, right? And if you call the min function and give it a vector as input, then it's going to return the minimum value inside of that vector. So if you look at the Vmax, V5, right? V5, the maximum value is 0.7952, 0.7952, right? And then Vmin is 0.1869, 0.1869, right? And this max and min function can return not only just the maximum and minimum value, it can also return the location of the maximum and minimum value, actually. The index, basically. The index. So for this particular example, the maximum value actually occurs at this 1, 2, 3, 4, the fourth index, right? And the minimum occurs at the fifth index, right? So if you would like the max or min function to return not only the value, the maximum and minimum value, but also the location, right? The location corresponds to that the index that corresponds to the maximum or minimum value. You can specify a second output, say ID max, right? And then ID min. Right? You can do that. Right? So in this case, let's still look at the V5, right? And then the maximum is the last one, the fifth, right? So Vmax is gonna be the last one, and then ID max is gonna be 5, right? And then Vmin, the minimum value is gonna be the second element, right? So ID min is gonna be 2, right? So those functions actually allows us to examine some characteristics about a specific vector very quickly. So now once we are equipped with all those understandings about MATLAB vectors, we can try to solve this vector analysis problem, right? So now we are actually ready to write our script for solving this particular problem, right? So vector analysis problem. So tool percentage signs is going to start a new section in your script, right? So let's examine this particular problem. Right? For 50 equally spaced values of this function in this region, it means that we do want the t to have a starting value that's fixed at 0, and then end with 2 pi, right? So in this case, the ideal way for generating this particular vector is by using linkspace, right? So what we want is 50 equally spaced values. That means 50 points. 50 points starting from 0, ending with 2 pi, and they are equally spaced. And so in this case, linkspace is the right function for us to call, right? Starting with 0 and ending with 2 times pi. So in mathematics, you can just write 2 pi without the multiplication in between, right? But in programming language, you must specify this multiplication, right? The star, right? And you don't really have a keyboard sort of letter for pi, this kind of mathematical Greek letter, right? In MATLAB, pi is just represented by these two letters, pi, right? And then you want 50 points, right? So 50 equally spaced values. So that's going to be our horizontal axis. Right? And that's t. That's the time, right? And then the function f equals to sine of t. We have used the sine and cosine, those trigonometry functions, but with a scalar as input, right? In our flowing circular channel example, for example, right, we looked at how to use those intrinsic functions, and we looked at how to use the trigonometry functions given by MATLAB. But all the inputs we were giving to those trigonometry functions were just scalars, right? But now here we're actually giving the trigonometry function a vector as its input, right? And then what Matlab is gonna do, right? What Matlab is gonna do is that it's gonna apply this sine function to each individual elements inside of the t vector of this input vector, right? And then it's gonna compute the sine of each of the individual element. And then the output of the sine function is going to be organized into another vector, right? And that vector is going to be f. So f is going to be just the result of applying the sine function component-wise or element-wise to each of the elements inside of t, right? And that's exactly what we wanted. We have 50 elements inside the t vector that are evenly distributed from 0 to 2 pi. What do we want to do is to actually compute the sine of the sine to apply the sine function to every value that's kind of evenly distributed between this range, right? And then the next so we have a t and a f, right? We have t and f, and then the question is that we have to determine the time at which the minimum positive value of ft occurs, right? What's actually the minimum positive value of ft? So what we want is to find all the positive values first, right? And the condition for that is f larger than 0, right? So if we actually index f using this particular conditional, then the result of this evaluation is going to be a vector that contains just positive values, right? And what we have to do is to actually find the minimum. What we have to do is to actually find the minimum. Right? So this conditional allows us to select all the positive values that's inside of this f vector, right? And then the output of this particular selection operation goes into the min function as the input. And then the output of the min function is going to be min val f. We're going to assign it to this variable, right? Min f. Let's just call it min f, right? Or f min. F min, right? F min is actually a Matlab intrinsic function. F pos in min, right? That's a positive minimum number, right? So we have found the positive minimum value, right? Positive minimum value, or the minimum positive value of f, right? But that's not exactly what the question is asking. It's asking us to determine the time at which the minimum positive value of ft occurs, right? The time is actually the location. It's actually the index, right? But the problem is that even though the min function is going to return the index, right? The index, but it's the index of this particular input vector, right? It's not the index of the original f vector, right? It's this filtered f vector, right? It's the index inside this filtered f vector, right? But that's not the index that we really want, right? What we want is actually an index into this original unfiltered vector, right? This original unfiltered vector. So how can we actually sort of get the index of that? Get the index of that, right? Again, let's see if we can use find function, right? What's going to be the condition for the find function, right? If it's f compare with f pos min, right? If we compare f with f pos min, and this comparison returns true, which means that we have found that particular element inside of this f vector, not the filtered f, but inside of the f vector, right? Let's give it the ID min, give it this particular index, right? And then, in order to actually find the time, let's call it t min. all we have to do is to use this ID min to index into the t vector. Don't forget, this f vector is computed component-wise or element-wise from every element inside of the t vector, right? So every f element has a correspondence with the t element inside of the t vector. So here we have found the index that corresponds to the minimum positive value inside of the f vector, right? And if we actually use this same index to index into the time axis, we are going to be able to actually retrieve the time, the t, that corresponds to the minimum positive f, right? Because f and t has this kind of one-to-one correspondence, right? And this way we have solved the first question, the A part. Let's give it a run and see what's actually the correct value, right? T min 3.1775, right? 3.0775, right? If we would like to actually just visually examine if this value indeed makes sense, we can actually make a plot of it, right? So let's just create a figure, and then let's call it a figure 1, and then make a plot of t and f. Let's just run it. Yeah. So minimum positive value, it's supposed to be either 0, the starting next, or at some location here, right? Some location here. And t min is what? T min is 3.0775. That's about here, right? Looks like it's the correct solution, right? So if we look at f1, that's what? That's 0, right? And then ID min, that's 25. That's 25. So f20 ID min is what? 0.0641. It's indeed a positive number, right? It's indeed a positive number, and it's probably it's a positive number, right? So it's not equal to 0, right? And it's actually smaller than all the rest of the positive numbers inside of this f function. And then now let's try to solve the second part of this problem, which is to compute average value of its negative values. So in this case, we have to find all the negative values first, and then compute the average of it. And here we're going to use another Matlab function that's called mean. So the mean function allows you to actually compute the average, right? So what we're going to do is go FAVE, the average. So negative average is going to equal to mean, and then f negative values. So f smaller than 0, that's going to be our condition, right? And at this point, we have completed the calculation of both questions. And then if we want to do a disk time of minimum positive value, and then num2 str t min, right? And then disk average of all negative values, num2 str f neg ave, right? And let's run it, and we will be able to actually find the correct solutions. So the average of all negative values, that's minus 0.62367, right? And then the time of the minimum positive value is 3.0775, right? And so we have actually solved this particular problem.